So, how are bearings used in engineering? In this presentation, I will explain how different bearings work, their applications, and their pros and cons. So what needs rotation or linear movement? Well, apparently a lot of things. We live in a moving world. Things that need to move include skateboards. The wheels need great support to spin as well as be intact. Car motors have a whole world of moving things under the hood, spinning tires under great weight. Airplane turbines spin immensely fast with great accuracy for the sake of the passengers in it. And most importantly, transformers. It has so many moving parts, all the joints are moving, the motors are moving, and the eyes are moving. So it is very clear how crucial the machine elements are and how the support of these movements should be studied. Movement and parts are necessary for machines to function. So bearings can help. What are bearings? They basically support moving parts by doing two things, allowing movement and supporting the load. For example, an airplane turbine is really heavy. That translates into a great radial load acting on the shaft. This can cause it to bend and even break. In axial load, the force acts parallel to the shaft, and this can lead to translation, which means it's not secure, and even friction between the shaft and the element. Luckily, we have solutions for these problems. For radial loads, we have journal or sliding contact bearings, and for axial loads, we have rolling contact bearings. So breaking the journal contact bearing down, it's basically just a shell and a shaft. The bearing here is the fixed element, and it can be secured by bolting it down. The journal is a moving element that can rotate. The space between the bearing and the journal is called the clearance. It is really small, but it is enough space to allow the viscous lubricant to work its magic. There's two things that this diagram is missing. Typically, there's an inlet here that allows one to inject lubrication if the bearing needs more. And these bearings also have a lining right here. It's typically of softer material, so that if the journal were to make contact with the bearing, it would wear out the lining first before damaging either the journal or the bearing. Well, how does it support radial loads? When off, contact between journal and the bearing is present. When it's turned on, it starts to rotate, and it pumps and drives the viscous liquid. Because the liquid is viscous, it tends to stick to surfaces, and as it gets driven under the journal, it forms this lubricant wedge, and that separates the journal and the bearing from contact and allow for great radial load to act on it without worrying about the wear it may cause if there was friction. The pros and cons of journal bearings. Because it can take great radial loadings, it is really suitable for heavy machinery. With its simple design, it's theoretically supposed to never wear out due to lubricant wedge and the backup lining. Here's an example. This is a crankshaft, and it's used by ships and cars to provide rotational power. Here's the shaft, and here's the bearings. The cons of it: the lube is like a picky child which needs the right element to behave well. There can be corrosion as a result of poor care of the lube. If it's hotter or faster than the journal can handle, the viscosity may decrease and the wedge may be lost. Here's the inlet where you have to pour the lube in, which you need a great supply of in order to maintain it. This is a crankshaft of a container ship. As you can see, it's incredibly large and it's very heavy, but it maintains and it works well because it can handle the radial loading. You can see this is the bearing right here. The shaft is going through it. And now onto rolling contact bearings. This is an example of one, and when we break it down into the components, the outer ring here is the fixed element and the inner ring here is attached to the shaft. The balls are what is touching both of them, and the cage is only there to separate them equally. The inner ring can be fitted very well to the shaft without having to worry about the friction because the balls are responsible for that. So how does it support axial loads? Well, let's think about how moving objects lose energy. In sliding friction, the two surfaces are moving with respect to each other. This causes kinetic friction and energy is lost. The friction is acting against the force. However, in a rolling friction, with the ball turning and rolling, the contact points only meet for a minimal amount of time. It is almost like static friction. The surface in contact practically, it doesn't really move with respect to each other, so it doesn't necessarily lose energy to friction. What does that mean? It means that the rolling contact's coefficient of friction is less than the sliding contact's coefficient of friction. The pros and cons of rolling contact bearing. Because of its low friction, it's more durable because of the less wear and tear. It can handle high speed movement and handle axial and radial loads, although it's more praised for its axial load. And it does not need lube in contrast to the journal bearing, so you don't need a great supply of that to maintain it. However, the cons include that it cannot handle heavy machinery like the journal bearing does, and because it's more complex, it's harder to fix it if you need to, and it's harder to get replacement parts and rebuild it. This is an example of roller contact bearing. In helicopter blades, this is the motor that runs it. The weight of the blade pushes on the bearing parallel to the axis, and it needs to go at high speed, so the roller bearings are really a perfect fit for this motor. Roller contact bearing can have different designs to meet different loading requirements. Here are 3 examples. The first one is angular contact. As you can see in the outer shell, the left side is thicker than the right side, and the same is for the inner shell. This results in a greater axial load in that direction, in the thicker direction, but it sacrifices the radial load. The cylindrical roller has cylinders replacing the balls and it rolls this way. This sacrifices the axial load but gives greater radial load. The tapered rolling bearing is kind of like the best in both worlds. So in the outer shell, you can see it is thin and it grows thicker, but the inner shell compensates for it. So wherever it is thick, the inner shell is thin, and wherever the outer shell is thin, the inner shell is thick. So this gives greater axial load and greater radial load. And that's about it. I really appreciate you listening to my presentation. I had a great time researching all this.